Hi, sorry. Today we're looking at stationary and progressive waves. This question I'd like you to have a go at to begin with is multiple choice question. What is the phase difference? So we need that in radians, okay? So in pi radians, between 2 points. They are 0.16 meters apart on a progressive sound wave of frequency 2.56 hertz, okay? And the speed of sound is 330 meters per second. So I'm just going to draw you what that might look like. 1 second. So what it's saying is you've got a progressive wave and you've got 2 points that are 0.16 meters apart. Now, I've made these points up. They could be anywhere on the wave, but they're 0.16 meters apart. And the question wants to know what's their phase difference in wavelength. So are they pi out, like half a wavelength out? Are they 2 pi out at the same place, or anywhere in between there? Okay, so pause the video and have a go at the question. Okay, so I'm going to show you how to figure out the answer to this. The answer is C. Okay, and I'll just show you how to do it. First of all, if we want to know what fraction 0.16 is of a wave, we need to figure out the whole wavelength. So we know that the frequency is 250 hertz. Sorry, 256 hertz. And we know the speed of this wave is 330 meters per second from the question. So we can figure out the wavelength by doing V over F. So that's 330 over 256, which gives me about 1.3 meters. So my whole wave from here to here, say, is 1.3 meters. So I know 0.16 is less than a wavelength. So I need to figure out how much of a wavelength it is. Okay, well let's do 1.3 divided by 0.16 and then that'll tell me how many times 0.16 fits in this. And the answer you get is about 8. So it's an eighth of a wavelength. Okay, now I know a whole wavelength is 2 pi. So if I do 2 pi divided by 8, it will tell me how much of the whole wave that is. So that cancels with that and you get pi by 4. So the answer is C. Okay. Right, so on to today's lesson. Stationary and progressive waves. Now, we need to describe the necessary conditions for the formation of a stationary wave. We need to deduce whether a stationary wave is formed by superposition, and then explain why nodes are formed in fixed positions. So, looking at the formation of a stationary wave. So again, you can press pause at different parts of the video and take the notes that you wish. Now we're going to talk about fundamentals here. So we're going to talk about waves on a string. And in fact, I'm going to pull this up. We showed you a little bit of this last lesson on the pictures I had of the person holding a bit of string. So if I have a wave, and then a boundary here, like let's say a guitar string. If I pluck my wave here or my guitar string here, the wave will go like this, rebound at the boundary, and then come back again. Okay, and it will keep doing that. Now, I'm actually going to turn this 90 degrees because it's a bit easier to draw it on horizontally. That shape is called the fundamental wave, okay, or the fundamental frequency. It's the lowest frequency I can make on a wave on a piece of string. So you have to make all of these the same length. So I'm going to do 10 centimeters. So the lowest frequency wave I can make on a piece of string, standing wave, is this one. Oh, that's so bad. Ignore that. I think 10 centimeters is too long. I'm going to try 8. I'm actually going to get a pencil because will be better. Okay, let me just plot my points. There we go. That's going to be better. So I'm going to draw a wave here, up, and then back down, and then the other side. So usually you draw the other side with a dotted line here. And you can see here I've got a node, and an antinode. I like to write this at the side. It spells nan, which is cute. This is called the fundamental frequency, okay? Or the first harmonic, or the fundamental mode of vibration, okay? It's the lowest frequency. Oh, sugar, sorry. I can make on a piece of string, okay? Now, I can make the next harmonic. So I'm going to, all of these have to be the same length. Otherwise you change the, when you change the length of the piece of string you're looking at, you get different harmonics. So this is 8 centimeters again. And this time, the next frequency I can make is going to be this one. So I've got can you see how I'm plotting out where I'm going to draw the wave just to make sure it's accurate? So now you can see in this one I had 2 nodes, and on this one I've got 3 nodes and 2 antinodes. So I've got a nanan. Yeah? Now what you should be able to see as well here is that this is half a wavelength. Okay? So it's pi, half a wavelength. Remember 2 pi is a whole wavelength. This is 1 wavelength. This is 2 pi. Yeah? So you've got a whole wavelength on there. Do you see? Okay, so the next one is going to be 1.5 wavelengths. So we're going to have, we just add another an on the end here. So we're going to have a nan, an. Yeah, so every time you add an an. So I've got 1, 2, 3, 4 nodes. Here I had 3, 1, 2, 3. Now I'm going to have 1, 2, 3, 4 nodes. So I need to, this is 8 long. So if I'm going to have 4, I'm going to have 1 there, 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 and there. You can see me plotting out where I'm going to put them. And in this way you can build up all the different harmonics on a piece of string. And then this one's going to go here. Okay. So you've got 1.5 wavelengths there. Now this is called the second harmonic, and this one's called the third harmonic. See if you can draw, pause the video, draw these out and see if you can draw me the fourth harmonic using this sort of nan thing to help you. If you pause the video, I'll go through how to do it in a second. Okay, so I'm going to add another an on the end here. So I've got nan, an, and it's the fourth one, and so I've got 1, 2, 3, 4, 5 nodes. 1, there's going to be 1 in the middle, 2, 3, 4, 5. Plot my maxima and minima. Okay, and then the other side. Remember, these aren't two waves, it's one wave that goes from here to here to here to here, okay? So I've got an an, and. And that's my fourth harmonic. So these are all the harmonics that you can get on string. They're basically notes. They're notes on a string, yeah? So they have different frequencies. This one is more frequent than this one. Okay. It is 1, 2, 3 times more frequent. Oh, sorry, 4 times more frequent. So that's number 1. It's twice as frequent, 3 times as frequent, 4 times as frequent. So you're changing the frequency of the wave, okay? So this fundamental harmonic has a frequency F0. Okay, the second harmonic will be 2F0. The third harmonic is 3 times that, because you've got 1, 2, 3 half wavelengths. And the fourth is 4F0. All right. And what's happening at these points? Well, this one's easier to talk about. At the nodes here, you've got a wave going this way and a wave coming this way. And at this point, they've met and there's a peak and a trough and they've cancelled each other out. So you get nothing. At this point, when they met, they were both at a peak. So you got a greater amplitude. It's like you've got the wave coming this way is at a peak here. And the wave that was going this way was at a peak here too. So they added together and made your maximum. And at this one, the wave coming this way was here. And the wave coming this way was also here. So they added together to make that. But at this point here, the wave that was coming this way was at the top. The wave coming this way was at the bottom. So they cancelled each other out and you got nothing. So that's what's happening when you're creating these standing waves and the harmonics on the standing waves. You're getting some places where they're completely cancelling each other out. And you've got some places where they're reinforcing each other to create maximum amplitude. And then the bits in between. Okay. So I've just been through that here. Okay, so that these lines and this is just for what I've just been through. And if you notice on my picture, I'm adding a half wavelength every time. Yeah, so you've got half a wavelength, 1 wavelength, 1.5, 2, 2.5, 3, 3.5, 4. So I'm always adding half a wavelength. Okay, and the distance between the nodes is half a wavelength. Now this is really important. This is the definition of a stationary wave, which is a wave, basically what we've just talked about, is trapped on a string. So stationary waves that vibrate freely do not transfer energy to their surroundings. They can't move energy from one place to another, okay? Like light waves from the sun transfer energy from the sun to the earth. These waves do not do that, okay? So stationary waves vibrate freely, do not transfer energy to their surroundings. So you need to write that as the definition if you're asked what stationary waves are. And you know it's really important to learn the definitions specifically as they are for exam questions. At a node, the amplitude is 0, so there's no energy at the nodes. At antinodes, the amplitude of vibration is at a maximum, so there's maximum energy at the antinodes. This is on the string, not in the surroundings. And because the nodes and antinodes are at fixed positions, the energy is not transferred along the way. So basically, you always get maximum energy here and minimum energy here. It's not moved along like in a progressive wave. Now we've just talked about the progression, the formation of the stationary waves, and I find this slide a bit confusing. But it's like here, this one's okay. So where the two waves are at a peak, you get a peak. Where the two waves are a minimum here, you get the maximum trough, okay? But here where you get cancellation at the nodes, the waves are at an antiphase. So you can see here they're pi radians out of phase. They're half a wavelength out of phase. But I think I explained that better on my diagram. Okay. Now, the amplitude of vibrating particle in a stationary wave patterns vary with position. So at a node, 0 amplitude. So basically at the nodes, these particles, these bits of string are not moving. They're staying stationary. An antinode, they are always moving with maximum amplitude, so it's going from back to forth to back to forth, and everything in between is between 0 and the maximum. And the phase difference between two vibrating particles is 0 if the two particles are between two adjacent nodes. So basically, if I have this node and this node, this particle here and this particle here have 0 phase difference because they're both moving up at the same time. Okay, they're both moving up at the same time because they're between two nodes. So they're not out of phase, they're moving at the same time. Okay, any two particles on this part of the graph will have 0 phase difference. Any two particles between these two nodes will have 0 phase difference. If I've got a particle here moving down and a particle here moving down, they're moving down at the same time, so they have 0 phase difference. But if I have a particle here on the left of the node and a particle here on the right of the node, they are moving out of phase. These particles are all moving up and these particles are all moving down on the string. So they will have pi phase difference, half a wavelength. They're going up and these are all going down. Okay, so the phase difference is pi radians if the two particles are separated by an odd number of nodes. So these two particles, one here and one here, are separated by one node, which is an odd node. Okay, so these are moving up and they're moving down. These two particles, one here and one here, they're separated by two nodes, so that's an even number of nodes, so they're both going up, up and up. So their phase difference is 0. But if I have a particle here and a particle here, they're separated by 1, 2, 3 nodes. So these are going up and these are going down. So their phase difference is pi radians. Okay. Right, last bit. This table compares stationary and progressive waves. So see if you can think about what does the frequency of a stationary wave change or stay the same? What does the amplitudes look like? What's the phase difference between two particles on a progressive and stationary wave? And I'll just go through the answers in a second. Okay, so on a stationary wave, the frequency, all the particles except those at the nodes vibrate at the same frequency. So the nodes don't move, but everything else all moves up at the same time or moves down at the same time. So they all have the same frequency. The amplitude varies from 0 at a node to a maximum at the antinodes, but the particles will just do their own. So if they're at amplitude, those particles all move that amplitude. The phase difference between two particles, we now know particles between adjacent nodes are in phase. So if all the particles are within two nodes, they all have the same phase, so phase difference is 0. Particles between the next nodes, so you've got a node in the middle, one's going up, one's going down, that's pi radians out of phase. On a progressive wave is one like on the C or in the question at the start of yesterday's lesson with the wave rope moving. Okay, that's just one wave. So it's like the particles are here and the wave is coming through. So on a progressive wave, all the particles vibrate at the same frequency. They'll vibrate at the frequency of the wave. And the amplitude is the same for all the particles. So the particles will go through the whole wave, okay? Okay. And the phase difference is, we've talked about this in a previous lesson, 2 pi d over lambda, where d is the distance apart and lambda is the wavelength. We actually did this equation at the start of the lesson, but in two different parts. Okay. In fact, I'll just show you that question again, but using that equation. We did this actually in a lesson with me at the start. This question at the start, once we've found this wavelength here, 1.3 meters, we can plug it into here to find phase difference. You're going to do 2 pi and you've got 0.16 over 1.3, and that will give you pi by 4. Okay. Okay, so I'd like you to just make sure you've got all those notes. and then I'd like you to have a go at this exam question. There's only 8 marks, so it should just take you 10 minutes, and I'll pop the answer on the classroom as well, and then you can mark it. Okay, thank you very much. I should see you next lesson, which is good. If you've got any questions, just email me, let me know. Okay, thank you, bye.